Hello friends, I welcome you all to this session on power plant engineering. In the previous lectures, you have seen that how to bring steam table data into Excel, how to use different functions to evaluate the uh, properties like pressure, volume, entropy, enthalpy, etc. for different pressures and temperatures in Excel. So now we'll be solving one problem, numerical problem. That means we'll be modeling one ideal Rankine cycle in Excel today. So you know that when we talk of Rankine cycle, we have one boiler, one turbine, one condenser, one pump, and let's say that the state just before the turbine is 1, at the exit of turbine it is 2, at the exit of condenser it is 3, and at the exit of pump it is 4. So inside the boiler, one constant pressure process is happening and another one is happening at the condenser side. Let's say this is point 1, then inside the turbine reversible adiabatic process happens, so this is 1 to 2. Then comes heat rejection in condenser, that is reversible isobaric, so it is 3. Then comes 4, that is reversible adiabatic process in pump, and then finally this one is the boiler process. Now let us draw this for a ideal Rankine cycle as well as solve it. So for that I have already set some parameters for you. So let's say that uh, the boiler pressure is 150 bar, that means 15,000 kilopascal. Condenser pressure is 2 bar, that is 200 kilopascal, and the inlet temperature to the turbine, that is this one here, is 550 degrees Celsius. And 1, 2, 3, 4 represents different states, 1, 2, 3 and 4. Okay. Now, first one is state 1. So if you look this state 1, then here, why not to crop and bring this there. So if you look this, state 1 is superheated vapor. So here also pressure is the boiler pressure, okay, and the temperature is basically the inlet temperature to the turbine, this one. Now I have to find out the enthalpy. You know, this is a single phase, so two properties will be required. So enthalpy I will be evaluating based on pressure and temperature for water. So this is the pressure and this is the temperature. So this is the enthalpy, that is 3450 at 0.1. Likewise, I can also evaluate the entropy based on pressure and temperature for water, and this is pressure and this is temperature. Okay. Now here there is no point of dryness fraction, because dryness fraction only means for between saturated liquid and saturated vapor. Saturated liquid it is 0, saturated vapor it is 1. So if you still try to find out dryness fraction, it will only give 1. Okay. Now comes point number 2. So in ideal condition, reversible adiabatic process is there. So reversible adiabatic means isentropic. So point 1 and point 2 should have the same entropy. Okay. So now what is the pressure at point 2? It is nothing but the condenser pressure. Okay. So what is the condenser pressure? It is 200 kilopascal. Now what is the temperature here? We all know it should be saturation temperature corresponding to the pressure. Okay. But I don't know exactly where this state is lying. It can be outside, it can be inside. So what I do, I leave the temperature as such for the time being. I only focus on entropy. So the entropy at point 2 is same as entropy at point 1 because of isentropic nature. So here what I'll do is I'll take the same value of entropy. Now based on this, I will be evaluating the dryness fraction. If the dryness fraction comes out to be uh, less than 1, then it should be inside, otherwise it should be outside. So how that can be done? So if you are doing it in pen and using pen and paper, so what you could have done is you have evaluated S1, you keep that S1 equal to S2, and then based on this condenser pressure you try to find out the entropy SF based on this pressure, plus x2 times then SFG, and then that's it. From here you can evaluate this x2. So we'll be using this as we are using Excel, so we can do it directly. That is in dryness fraction x based on pressure and entropy, let's say, for water. So this is the pressure and this is the entropy. So the dryness fraction at point 2 comes out to be as 0.892114. So now it is clear to us that the state is inside in the vapor dome. Okay. Now we can now evaluate the temperature, because this should be saturation temperature. So what I can do, I can use saturation temperature, which in principle, let me do this. Tsat corresponding to pressure for water, and let us take this. It is coming out what, 1. So what I'll do, I'll evaluate this temperature based on pressure and entropy, let's say. For water, this is pressure and this is entropy. What it should give, it should also give this same value. So you can see that it is giving us the same value, doesn't matter. Okay, now comes the enthalpy. Okay, so enthalpy based on pressure and entropy, okay, for water. So this is pressure, this is entropy. So this cell is M and this is M7, so it is M7. So this is the enthalpy at point number 2. Now comes point 3. So again, this is saturated liquid and the pressure has to be condenser pressure. So let us take the same value, and then comes the temperature. So this is going to be saturation temperature corresponding to the condenser pressure. So this is the one. Then comes the enthalpy. Now this is saturated liquid, so enthalpy of liquid has to be evaluated with respect to this pressure, that is condenser pressure. Then the entropy, that is saturated liquid entropy with respect to pressure. This is the one, and that's it. If you try to find out the entropy, the dryness fraction at this point, it should come out as 1. Let us do it. Dryness fraction based on pressure and let's say entropy. Okay, for water, so this is the pressure and this is the entropy right now. So it is coming out as 0. So not 1, sorry, 0, because this is saturated liquid line, and for saturated liquid dryness fraction is 0. For saturated vapor, dryness fraction is 1. Now comes the point number 4. Now what about this line 3 to 4? This is saturated, sorry, this is reversible adiabatic. So adiabatic means entropy has to be same. Another thing, this is the boiler pressure. So pump is doing what? Pump is transferring the fluid to a higher pressure, so that, or increasing the pressure of the fluid so that it can enter the boiler smoothly. So this point number 4 should have the same entropy as point number 3. Also, the point number 4 should be the boiler pressure ideally. So this is same as the boiler pressure, that means 1. Once this has been done, then the entropy. So entropy should be same as the entropy of point number 3, and once this has been done, you can find out the temperature, enthalpy, whatsoever you can want, whatsoever do you want. So this is enthalpy based on, let's say, pressure and entropy for water. So this is pressure, comma, entropy cell is M, so it is M9. Okay, the same thing you can do for temperature also. Temperature with respect to pressure and let's say entropy also. So this is pressure, okay, this is entropy, okay. So you have your temperature as well. So you have fully now evaluated pressure, temperature, enthalpy, entropy, all the cardinal important parameters for the Rankine cycle. Okay, now let us say I want to evaluate the turbine work. Okay, so what is the turbine work? Turbine work is nothing but the enthalpy difference between point number 1 and 2. So it is H1 minus H2. So this will give me turbine work in kilojoule, sorry, yes, kilojoule per kilogram. Then comes the pump work. So pump work is what? It is H4 minus H3. So what is H4? This is H4 minus H3. So this is my pump work. Now heat added, that is Q1, heat added in boiler. So that will be equal to H1 minus H4. So it is H1 and then minus H4. Then comes Q2, that is heat rejected in the condenser, it is H2 minus H3. So it is H2 minus H3, and all the parameters are in kilojoule per kilogram. Now, if you want to check whether you have done it correctly or not, so you know that net work output should be equal to net heat input for a cycle. So let us insert one symbol for sigma. I don't know whether it is there. So net work done first, and then we will be doing what? We will be evaluating net heat transfer also. So net work done means work done by the turbine minus work done by the pump. Okay, work done by the pump on water and work done work transfer from the turbine. So it is Wt minus Wp. So it is Wt minus Wp. What about sigma q? It is heat added minus heat rejected. What is heat added? It is Q1. Heat rejected is Q2. So now you can see both are coming same. That means the net work output in a cycle should be equal to net heat input, and it is being done. So let us, okay. Now what else I can do? What I can evaluate the efficiency of the cycle. So the efficiency is normally written as 1 minus Q2 by Q1. Okay, so it is 1 minus heat rejected by Q1. And now you can do what? You can convert this into percentage. So this is 33%. The same thing you can also do with respect to, so this is with respect to heat transfer, and now we'll be doing with respect to net work output. So with respect to net work output, it is net work divided by Q1. So again, you can find out the percentage. So this is how you can model your this what we call it Rankine cycle in using your Excel. Now what we can do is we can also draw this cycle uh, here, but for that what is required, this point and this point is also required. So what I'll do, I'll write 5 and 6. So let's say this is 5 and this is 6, and what is required? Pressure. So pressure at point number 5 is the same as boiler pressure, so it is the 1, and the pressure at point number 6 is again same as the boiler pressure. Okay, then this is my point number 5. So the temperature here should be the saturation temperature corresponding. So this is Tsat corresponding to this pressure. The same thing we will be doing for this. Okay. Now once this has been done, I am evaluating what? I am evaluating Ts. So S is required. So entropy of, so here it is saturated liquid. So it is SL corresponding to pressure. I am evaluating. Oops, I have done something wrong. So corresponding to pressure for water. This is the one. Likewise, this point, if this is 6, so this basically is the saturated vapor. So it is entropy of saturated vapor based on pressure for water. So this is the pressure, and that's it. So let us also increase the font. Okay, now we will be drawing our cycle. Okay, so look very closely. So first thing, we will be drawing this 1 to 2. So it is 1 to 2. So what is there in the x-axis? It is entropy. So S1 and then hold control, and this is S2. Then y-axis, it is temperature. So T1 control. Oops, sorry, I have done it wrong. Again, I'll do it. So it is T1 and then T2. Okay. Now if you look, so this has come. Now 2 to 3, again select data. So add. So it is 2 to 3, and then x-axis it is S2, S3, and y-axis it is T2, T3. Okay. Again I'll add, and then 3 to 4, then 3 to 4. So x-axis it is S3, S4, and y-axis it is T3, T4, and that's it. Then this is what, 3 to 4. Okay, then 4 to 5 I will be drawing. Add, this is 4 to 5. I don't know whether it will come 4 to 5 or give some date, doesn't matter. So 4 to 5. So this is S4, and then press control, then S5, then temperature, then it is T4 and then T5. Okay. Then what? Then 4 to 5 we have reached, then from 5 to 6. So from 5 to 6. Then this is 5, S5 and then S6. Okay. Then temperature T5 and T6. Okay. And then add 6 to 1, that is this particular portion. Now we will be closing the cycle 6 to 1. So S6 and then S1 and then here T6 and then T1. Okay, okay, okay. So friends, now here if you look closely, this is your Rankine cycle. Now what is the problem? There is no problem as such, only with the color. So let us change the color. So make it red. This also I'll make red, let's say, and this one also I'll make red. Okay, and this one I'll also make red, so that you can view it properly. Now if you look this, oops, this is your temperature entropy diagram for this particular basically for these parameters. Okay, now you can see that you are not able to see this 3 to 4 here. Why? Can you tell? Yes, you have guessed it right, because the turbine work is 981 and the pump work is 15.6. If you try to compare that how much turbine work is there in comparison to pump work, so it will come out as 62.7% more. So this line is 62.7% more in comparison to this, or this pump work is 62.7% less. So how can you see it? That's why you are not able to see. And if you want, now you can do lot many things. Let us remove it for the time being. Oh, why it is not coming? Okay. So now what you can do, you can play with parameters, because you have already developed a small simulator for you. So now if I increase the boiler pressure from 15,000 to let's say 20,000 kilopascal, now you can see what will happen. The same thing you can do. If you want, you can reduce from 20,000 to let's say 12,000. Oh, sorry, 10 I have increased. This will happen. If you reduce it further to let's say only 10,000, this will happen. If you increase the condenser pressure from 200 to let's say 1000, and at the same time you will also notice, now this is something wrong, because this has to be modeled correctly. This we have not handled yet. So let us keep to 700 or maybe lower, let's say 800 only. Oh, below 500, let's say. Oops. Now, so basically, now once you change the parameters, what will happen? These values will change. And once these values will change, you will be able to appreciate the impact of these onto different parameters. So what I'll do in the next lecture, so far you have only modeled an ideal Rankine cycle. In the next lecture, we will be modeling one real Rankine cycle, where so far it is reversible adiabatic pump compression and reversible adiabatic expansion in turbine. But what will happen if they are not reversible adiabatic? Then we will be having some different thing. So this will be handling in the next topic, that how to model a Rankine cycle in which the turbine and the pump efficiencies are also there. And then we will be trying to understand the impact of pressure, boiler pressure and condenser pressure on the efficiency of Rankine cycle. Okay, and then we'll be moving to our next topics. So thank you very much for watching it in this lecture till this point only. Thank you.